So the experiment that we've just seen is going to be the canonical problem that we're going to begin our study of deformable bodies. And so it's really the problem of bars under one-dimensional axial loading. And what we're going to try and do is take the observations that we've just made and turn them into a full mechanical theory that allows us to describe the complete behavior of that system there. Okay, so that's the goal. And the starting point is going to be kinematics. So kinematics is the science of motion, and what we observed visually was motion in the experiment, and we're going to try and take that information and turn that into the starting point for our theory here. Okay, so what we saw was that if we took the bar and we applied a load to it, that it deformed, and there was motion in the direction in which we applied the load. There was also motion transverse to the direction that we applied the load, but the really dominant part of the motion was the motion in the direction of the load. So let's say the x direction. So we'll define a coordinate system x that is in the direction of the long axis of the system, which is the same as the direction of the load. Now, the main observation that we had was that if we looked at given material points in the system, that they had a displacement. So in other words, when we deformed the body, a given material point, which I've labeled here, is going to move to a new location over here. And to each material point, I can set a function, u of x, which describes the displacement of the system. So u of x is a function, and for every point in the body, no matter which point I'm looking at, it's going to have a unique value, and that unique value is going to tell me how much the material point moves under deformation. So we call this a displacement field, more precisely. It tells us the field of displacements in the entire body. And what we'd like to do is turn this into a mechanical theory just from this observation. And the other part of the observation is that if I look at a plane section, after it deforms, it remains planar. So that's the plane section remains plane assumption that we had from the experiment. And together, these two ideas, very simple observations, can actually be used to construct a rather complete theory of the behavior of bars under one-dimensional axial loading. Now, displacement characterizes the motion, and it does it in a very straightforward way. It's what you see with your eyes. There's an associated concept known as strain, and strain characterizes relative motion. And the standard definition of strain is constructed out of, say, taking a bar, you apply a load to it, and it's going to change its length. And the strain is defined as the change in the length divided by the original length. And so this is kind of a definition of sometimes what is known as average strain. Okay. Strain turns out to be a more meaningful measure of motion when you're trying to understand the demands that you've placed on some type of material system by applying loads to it. It measures if something also, it tells you whether it's elongating, in other words, that the spacing, suppose it's a crystalline material, the space between the atoms is getting larger, or is contracting, the space between the atoms is getting narrower. So there's a it tells you other things that displacement doesn't tell you. Also notice that the strain can be zero even if the displacement is not equal to zero. So it provides you a little bit of a deeper concept of what's going on in the material when you deform it. And an example of the case where you can have zero strain even if the motion is non-zero is the rigid body motion. Suppose I take a body and it has a displacement field that's simply a constant, say 5 inches, the whole body just simply shifts over. So the right end moves 5 inches over, and the left end also moves 5 inches over, and any point in the middle also moves 5 inches. Well, the change in length of the body is 0 in this case, so the strain is going to be equal to 0. So this is just a simple example of where strain is 0. There's really no demands placed on the material, even though the motion is not equal to 0. So knowing the displacement field is very helpful, but the strain field actually tells you something, or the strain tells you something about the material itself. Now, the definition I have for strain right here is an average definition. It's not as precise as our definition for the displacement field, but we can improve that a little bit. So But first, just very quickly, notice that strain is non-dimensional. It's length over length. And typically, the numbers that you see for strain are rather small. They're things like 10 to the minus 6, which we would call microstrain. Sometimes they get a bit larger, millistrains and things like that. And occasionally they can become order 1. So that would be if you had a very soft material that you're applying a deformation to, say a rubber band or something, then you would get a large value for the strain. But typically the values of strain are small numbers, and most of what we're going to do is going to be restricted to the infinitesimal strain case. So these are strains that are, say, 10 to the minus 4 or less. And this will really simplify the equations if we assume that the strains are small. Many terms can be ignored, and you can get to much easier results when trying to analyze something. If you do an analysis and you find out the strains are large, then you'll have to go back and revise the calculation using what's known as a large deformation or large strain theory. Now, let's look at just one small refinement of the concept of strain. So we have this definition, which is delta L over L for strain, and it gives an average definition of strain. But let me consider a bar of material, and let me examine just a small piece of the bar. So it has some length delta x, and it's located someplace along the length of the bar. If I examine this little chunk of material and think about the bar deforming, then the material on the left end will have a deformation, and let me just call that u of x. So we'll take x to be the coordinate of the material on the left side. And the material on the right side will have a motion or displacement u of x plus delta x. So u is some displacement field for the bar. And now we can talk about the strain of this little segment of material, and that would be its change in length, which is the difference in the displacements. So u of x plus delta x minus u of x divided by the original length of the segment of material, which was delta x, and that gives me a measure of strain for that segment of material. Well, I can take the limit as the size of the segment goes to 0, and this little combination of terms, well, that's just the definition of the derivative in the limit as delta x goes to 0. So I get that the strain at some given point x, so the strain field itself, is just simply equal to the rate of change of the displacement field. So this gives us a point-wise definition of strain. It's a little bit more useful, we'll see as we move forward. There's also a sign convention for strain, namely that if the strains are positive, then you have locally elongating material, and if the sign of the strain is negative, you have locally contracting material. So just like we had a sign convention for the internal force diagram, we also have a sign convention for the strains. And we can also, if we want, we can make strain diagrams. We can also make displacement diagrams too. So we have internal force diagrams that we can draw. It tells us point by point what the loads are inside a material. We can make a graph of the displacement that tells us point to point, point by point, what the motion of the material looks like. And we can also do the same thing for strain. Now, there's a related concept to strain which is known as stress, which is sort of a force-like quantity that is also a relative quantity. And so let's consider a bar that I've applied a force R to, and the definition of the stress is the force normalized by the area over which it acts. So the area over which the force is acting over here is this little bit of area here. And so if I divide the internal force at any given cross-section by the area, then we get what's known as the stress. So the other way to think about that is that the stress is the magnitude of a constant distributed load over the cross-sectional area that corresponds to the internal resultant force R. The sign interpretation that we had for the internal forces also holds for stresses. So positive stresses are tensile, negative stresses are compressive. Stress has units. So the strain is non-dimensional, but the stresses have units. In the U.S. customary system, we usually talk about pounds per square inch, PSI, or thousands of pounds per square inch, so KSI. In the international system, the SI system, the standard for stress is Pascal, so Newton per meter squared. More typical in civil and mechanical engineering or aerospace engineering is megapascal, so MPa, and so that the convenient definition of that is newtons per millimeter squared. Okay, now we have these point-wise definitions for displacement and strain. It's also useful to have a point-wise definition for equilibrium, and we actually need that when we want to extend concepts of equilibrium to deformable systems. You'll recall that for a general body to be in equilibrium, every subset of the body has to be in equilibrium. So the net resultant force acting on the body has to equal 0, and the net resultant moment acting on the body has to equal 0. So we're just doing a one-dimensional problem here, so we're only going to worry about forces and only forces in the x direction. But let's look at sort of a general case here. Suppose I have a bar, I've applied some kind of, say, distributed load, we'll call it B of x, so we'll call it a body force, and it's force per unit length, and maybe there's a force on the end of the bar. And let's look at what it means to say that the system is in equilibrium. So what I'll do is I'll go ahead and look at a small bit of material of the bar. So it'll be located at a position x and have a length delta x. If I draw the free body diagram for the bar, on the left side I have the internal force r of x, and on the right side I have the internal force r of x plus delta x acting. And then in the middle there's this body force acting onto the system. And the actual force there is going to be the integral of the body force from x to x plus delta x. So I have three forces acting on this little segment of material. I have the two internal forces from the left and the right, and I have the body force in the middle. So if I sum the forces in the x direction, set them equal to 0, I have r of x plus delta x minus r of x plus b times delta x. So I've approximated this integral here by b times delta x. And I'm going to take the limit as delta x goes to 0, so it's not going to matter mathematically. So I'll divide through by delta x, and then I'll take the limit as delta x goes to 0, and what I find is an expression for equilibrium at a point in the system. It says that the rate of change of the internal force plus the body force has to equal 0. And this is going to give me equilibrium point by point, and so that's going to satisfy my requirement that for every subset of the body, in this case every subset of the body means every material point of the body, is in equilibrium. If I want, I can replace r of x by the stress times the area and have an alternate version of the equilibrium. But in either case I have a point-wise expression for equilibrium in the bar. And so this is what is needed when you have a deformable body. You need to have equilibrium point by point in the body. Okay, so let's have a look at where we are so far. We have our kinematics, and our kinematics are given to us in terms of two quantities, the displacement field and the strain field, so U and epsilon. We have our kinetics, which is given to us by the internal forces or the stresses. And we have our stress resultant definition, which connects the stresses sigma to the internal forces R through the cross-sectional area A. And we have a strain displacement relationship, which connects the strain field to the displacement field. And we have an equilibrium equation, which tells us the requirements for the forces to be in equilibrium. So in total, I have 4 unknowns in my system, and I have 3 equations. And that tells me that I need one more relation to close the system of equations. So we have linear equations, and so I'm going to need 4 equations for my 4 unknowns. And the missing piece of information in the setup is the constitutive relation. I haven't said anything about the behavior of the material. So the constitutive relationship for a material is the relation that connects the stresses to the strains, and simply sometimes called the stress-strain relation. The most basic stress-strain relation, and the one that we'll use most often in this course, is the linear elastic relationship. So it just says that the stress is linearly related to the strain, and this is sometimes known as Hooke's law. And when we say elastic, what we mean is that if I'm loading the system, I'm going to go up this line, and if I start to remove the load, I'm going to go straight back down. So when I release the load, I'll always be sitting at 0 strain, 0 stress. So this is the most simple stress-strain relationship that one can have. And written out in equation form, it says that sigma is equal to E times epsilon. So E is the standard symbol that we use for the slope of this line, and it's known as the Young's modulus. It's something that you can look up in handbooks for various types of materials. The range of the Young's modulus can go as high as a terapascal for something like diamond, and it goes down low, say 1 megapascal for soft polymers. It can even get smaller than that. It can also get slightly larger than a terapascal too, but that's the basic range. If you're working in the U.S. customary system, that's something like 150 million psi to about 100 psi. A very common example would be something like steel. Steel, the modulus is roughly 200 gigapascals, so GPa, which is also roughly 30 million psi. So those are good numbers to kind of keep in the back of your head when you're thinking about the value of the Young's modulus. Let me point out also, though, that mechanical forces are only one way to generate strains in a system. So you can apply a force, you'll have a stress in the system, that's going to produce a strain, say through the Hooke's law. But there's other ways to also induce strains, and when you have other ways to induce strains, you also have modifications to the constitutive law. One way of inducing strain is, for example, think about taking a dry sponge and immersing it in a bath of water. Well, it's going to swell, so its dimensions are going to change. There's displacement, and if you have relative displacement, you'll also have strain in the system. Another common way of generating strain is to heat or cool something. So if I take a bar and I heat it up, it will typically expand, and so its dimensions will grow, so I'll have displacement and I'll have strains in the system. We'll work sometimes with this thermal case here. In the thermal case, the strain can be generated in two different ways. We can apply a mechanical load, and we'll have stress over the Young's modulus gives a strain, but we can also change the temperature, and that also gives a strain. And the basic relationship is by multiplying the change in temperature by the coefficient of thermal expansion. The usual symbol is alpha for that, and added together we then get the total strain of the system. So we have the mechanical strain, which is sigma over E, and then we have the thermal strain, which is alpha delta T. Added together, that gives us the total strain in the system. So this is also a constitutive law that we will sometimes employ in our examples. Typical values for the coefficient of thermal expansion tend to be things on the order of 1 microstrain per degree Celsius, so that they're small numbers. You don't see it with your eyes, but it's something that can be very important in terms of the mechanical behavior of a system. Typical values, for example, say iron is 12 microstrain per degree Celsius, graphite is minus 0.6 microstrain per degree Celsius. So the coefficient of thermal expansion can be both positive and negative, though most materials have positive values. There are a few materials that have negative values. So probably the most common material that has a negative value is water near the freezing temperature. There's some other material behaviors that are sort of important to know about and keep in the back of your mind as we move through the course. If you have ceramic materials and you deform them, you have typically a linear stress-strain response for the system. If you have elastomers, they have a nonlinear response. So those are things like rubber bands and things of that nature. There's another type of material behavior which is known as elastic perfectly plastic. So this is an idealization, actually, of real material behavior, but it's an important model that you hear about. And this is applicable to ductile materials. And in this case here, what happens is you have a response where it's initially elastic with, say, a Young's modulus E, but then at some point you have actually constant stress values. So as you continue to strain the material, the stresses don't change. And this is known as the yield point. But if you reverse the direction of the strain, then you have what's known as elastic unloading. So you have this sort of very complicated type of behavior of the system. I should mention with the ceramics, you have other phenomena. So for instance, the ceramic can fracture. So when you apply deformation to ceramics, if you put too much tensile strain, so positive values of strain onto the system, they'll likely fracture and break apart. Elastomers will do the same thing. If the strains get sufficiently large, they will also snap. Most materials will have that type of behavior. If we look at metals, for instance, the real behavior of metals, so we have this idealized behavior, elastic perfectly plastic, but real metals have much more complicated types of stress-strain behavior. So this, for instance, would be an example of high-strength steel, where it starts off elastic, but then you get some type of nonlinear behavior, and then it eventually fractures on you. So there's a yield point, as it's called. That's sort of the end of the linearity regime. So below that you have sort of a Young's modulus. It goes nonlinear. You have some very complicated deformation processes, and then eventually it fractures on you. Other types of metals, so for instance low carbon steel, they have other types of behavior. They'll be linear, but then they'll yield at some point, and then maybe you'll have something that looks a little bit constant, so it looks somewhat like the elastic perfectly plastic material, but then maybe it starts to harden again. There'll be a peak stress value, which is usually known as the ultimate stress, and then eventually, if you deform the material enough, it will fracture on you. So you can have very complicated material behavior. We will primarily be sticking with the linear elastic case. Just a bit about numbers. Typical yield values for metals, they tend to be on the order of hundreds of megapascals, or in the US customary system, tens of thousands of psi are common values. Things like 40 KSI, 80 KSI are common values for yield of steels. And often one of the main questions in analysis of deformable mechanics is the question of, well, has the system yielded or not with respect to the loads that are being applied to it?